So today we're gonna dig into the review document, and I've got some problems here selected that I think would be useful to just check how we're doing. And if any of these give you trouble, then they demand your focus. Okay, but before we get started, I want to open the floor for any specific problems that you guys may be having. Get those dealt with right away. It's okay. Now, just a kitty cat. All right. If not, let me share the review document key. Here it is. And there we go. All right, so let's see, let's back up to the top. And yeah, number one. Let's see, is this going to require no, this is a good place to start. All right. So we're going to look at number one. And this is a word problem that doesn't tell you what the balanced equation is. You got to figure that out yourself. It does tell you that calcium metal reacts with oxygen gas. Right. Calcium, a solid, reacts with oxygen. Now, if you don't remember that oxygen is diatomic, then you're dead in the water. It's a diatomic gas, and the problem says it forms calcium oxide. So you got to be able to write calcium oxide. Okay. Calcium is an alkaline earth. It's a 2+ charge. Oxygen is a chalcogen with a -2 charge. So you only need one of each. So now we've done, the first step is to write the elements and the compounds correctly in the form of a reaction equation. Then we need to balance it. Right? For something this simple, I don't even write the budget out. Because if you've got one element here and one element there and a compound over there, it's fairly simple to get them to balance. You need 2 oxygens over here. That makes 2 calciums. Now you need 2 calcium. So that's easy to balance. Now that we've got a balanced equation, we can say, what does the problem tell us that we're given to begin with? Well, we react 5.66 moles of calcium and 4 moles of oxygen. All right. Now, what's the question? The number of moles of oxygen left over after the reaction is complete. So we want to know, one thing that's also telling you is that if oxygen is left over, that must mean that it is excess. And this one is limiting. All right, we can prove it to ourselves. We're going to have to do some calculations anyway. So with 5.66 moles of calcium, how many moles of oxygen are required? Right. If we take 5.66 moles of calcium and we want to know how many moles of oxygen are required, then we need coefficients, 1 and 2. So 1/2 of that number, which should be, let's see, 283. That's how many moles of oxygen will be required. So yes, in fact, it is excess because we have 4 moles and we only need 2.83. So how many moles left over? You just subtract. We're going to use that many. That's how much remains. Okay, that's why the answer is A. Any questions? Some of these word problems give you some useful information that it's not on the surface. You have to sort of read into it. Looks like my board's going to be difficult today. A lot of ghosting going on. All right, the next one I checked off. I better mark these as I go, so I won't double back and try to do them again. Is number 3. Okay, for this one, we're actually given the balanced equation, and I see a mistake. 2 waters, where the 2 in the water should be a subscript. So I need to fix that. But we're given this balanced equation. Right there. And the question is, what number of moles of hydrogen will be produced when 4 moles of sodium is added to 1.2 moles of water? All right. This is almost the same type of problem. In fact, it is the same type of problem as number 1, only we don't have to balance this equation. You know what? Let's write it the way they're given it. Then I'll say a couple of words about this. First of all, if this were the simplest whole number ratio, it would be 1, 1, and 1. Right? So that leads me to believe that maybe it's not balanced. So let's check it out. The way it's written, 2 sodiums, 4 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens. That equation is not balanced. So what I would do is get rid of the coefficients and balance it. Okay? So we got 1 sodium, 1 sodium. We need, you know what? I left something out, didn't I? Wrap around to this one. Plus H2. That makes all the difference in the world. So now we have 1 sodium. We have an oxygen here, an oxygen there, and 2 hydrogens there, and 3 hydrogens. So we're going to have to balance this equation. So let's set up our budget. All right. We got 1 sodium, 2 hydrogens, 1 oxygen. Over here we have, maybe it is balanced now. Let's do it anyway, just for fun. 1 sodium, 3 hydrogens, and 1 oxygen. So let's see this. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So now, when you have hydrogens on both sides, but this hydrogen's in 2 different places. So if we were to say 2 in front of this, that would make it even now. It'd be 4. Right? So now we have 4 hydrogens, 2 and 2. And if we make 4 hydrogens over here, it's 2 like that. But now we have to balance the rest of it. So we have 2 oxygens, 2 sodiums, there we go, 2, 6, 7, 8, 2, 4, 6, 7, 8, okay? And on this side, we need 4 hydrogens, got that, 2 oxygens, and we need 2 sodiums. Okay, so it was balanced after all. My mistake was I didn't see that hydrogen hanging down there on the second line. All right, now that we know that it's balanced, we can proceed with the rest of the problem. What else are we given? 4 moles of sodium and 1.2 moles of water. 2, 0? No, just 1.2. No, that's only 1. Here we go. Now, what number of moles of hydrogen will be produced? So we're looking for this one. Okay? So in this case, we do have to determine which is limiting. So in this case, I'd use my preferred method and say, if all of this is used, how many moles of hydrogen will be produced? And then go back and say, in another world, if all of this is used, how much hydrogen is produced? And the limiting one is the one that produces the least amount of hydrogen. And once you've done that, you already have your answer. Because the question is how many moles. We're going to do that calculation twice. So for 4 moles of this, we need a conversion factor that will do that. And that's understood to be moles and moles. So 1 of these and 2 of these makes 2 moles of hydrogen. Then we go back and do it with this one. 1.2 moles of water. Now we have water that has to be canceled to leave us with hydrogen. Right? This canceled before, now this one cancels. So 1 hydrogen and 2 waters again. This is 0.6 moles of hydrogen. So which one's limiting? Water. Water limits this reaction. Water will completely run out and produce 0.6 moles of hydrogen. That's why the answer is A. Now, how many moles of sodium are actually used in this one? We're not using all 4 moles. So how many moles of sodium are actually being used? Well, you go back here. If you're using up all of this, then the number of moles of sodium that are being used is 2 to 2, which is 1 to 1. 1.2 moles of sodium are being used. So you're going to have how much left over? You're going to have minus 1.2. Right? So it'll be 2.8 moles of sodium remain. That wasn't one of the questions, of course, but I couldn't resist. So we'll use up all of our water, and we'll have 2.8 moles of sodium left over. Right? So, just as a side, this is an extremely exothermic reaction. Sodium, you throw sodium into water, take a big chunk of sodium and throw it in your neighbor's swimming pool, it'll explode. And may even, if the chunk is big enough, it may even crack their pool. All right. In that case, water's excess, right? There's plenty of water. So all of that sodium will be consumed. All right, that was number 3. Let's see. Number 5 I want to look at. Okay. This looks to be the Hobber process. So nitrogen gas, hydrogen gas makes ammonia. This one's fairly easy, I think. This is, in fact, this one's not even as difficult as 1 or 3. We'll just do it for completeness, and so it's recorded. So we've got this reaction plus 3 hydrogens. Even balanced it for us. There we go. And we can check it for balance. 6 hydrogens, 6 hydrogens, 2 nitrogen, 2 nitrogen, we're good. Now, if we're starting off with 1.21 moles of hydrogen, and we want to know how many moles of ammonia could be produced, then we just need to know the coefficients, right? 1.21 moles of hydrogen converted to ammonia, right? Hydrogen cancels. So we have 2 here and 3 here. So it's 2/3 of 1.21. Uh, 0.8, 3 significant figures, 0.807. Of ammonia. All right. That's why C is the answer. We probably should have started with that one. That was a lot simpler than 1 and 2. Okay, 6 is a little more involved. All right, so we'll go to that one next. Somebody else didn't show up. I heard my computer talking. Okay, nothing there. All right, number 6. All right. Consider the following unbalanced equation. So we're heads up, this equation is not balanced. Then if 1.7 grams of ethanol, That's what this is right here. C2H5OH is ethanol. Reacts with 11.2 grams of oxygen. And you can, by deduction, you can say, you know what oxygen is, right? And there are only two reactants, so the other one has to be ethanol. And how many moles of carbon dioxide are produced? Right? So we have the compounds are already written for us, and you can check to see. Ethanol is an organic compound, so you just have to take their word for it. Oxygen, you know. Carbon dioxide, you know. Water, you know. And they look kosher. So we have this one, C2H5OH plus oxygen yields carbon dioxide and water. Right? So we can set up our budget. We have carbon, hydrogen, and oxygen. That's it. Right? 2 carbons, 6 hydrogens. Don't lose track of those hydrogens. 6 hydrogens and 2 oxygens. So it's 8, 9, 10, 2, 3, 4, 9, 10, 11. Oh, I missed one somewhere. I missed that oxygen, didn't I? Three oxygen. Now on this side, we've got 1 carbon, hydrogens, 2 hydrogens, and 3 oxygens. And that's 5, 6, 2, 3, 4, 5, 6. Okay, now we can work on balancing. Let's see. I don't see anything that's advantage to starting someplace else. We could do, since hydrogens occur here only and here only, we could do the hydrogens first. So we need 3 of these, which makes 6 hydrogen. But it also makes 3, 4, 5 oxygens. Right? And we need 2 carbon. 2. Now we've got 4 and 3 is 7. We got, 7 oxygens. So let's see if I counted them all right. 13, 14, 15. So 2, 6, 12, 13. So I'm missing something. Let me count them again. 2 plus 4 is 6. Plus 6 is 12. Oh, plus 3 is 15. 13, 15. Okay, that's good. 8, 11, 2, 7, 8, 9, 10, 11. Okay, so we've got carbon and hydrogen balanced. We need to balance oxygen. So, but we need 3 total oxygen. We've already got 1 here. So we really only need 5 more. No, we need 6 more. So if we put a 3 here, that makes 6 plus 1 is 7. There we go. Now we're balanced. If you can't get past this point, then you can't work the problem. And we can check it to be sure. 2 carbons, 5, 6 hydrogens. 1 plus 6 is 7 oxygens. So we have 4 oxygens and 3 is 7. So we are balanced. Now what are we given? 1.7 grams of ethanol. And 11.2 grams of oxygen. All right. The question is, how many moles of carbon dioxide are produced? So when you have a problem like this, where you've got 2 known amounts of reactants, well, where there are only 2 reactants, but if they're all known, then one of them is going to be limiting. And if the question is asked for a product, then my preferred method is the way to go. If we say, how many moles of carbon dioxide will this produce if completely consumed? How many moles of carbon dioxide will be produced if this is completely consumed? Then compare the two. And when you got the comparison, the smallest one is your answer, right? Because we're looking for the number of moles. So let's take this, and remember we have to make moles. If you don't have moles, you can't go anywhere in an equation. So moles and grams as a quotient always means molar mass. So the molar mass of ethanol is our first target. 2 carbons, 12.01 times 2, then 6 hydrogens, which is 6.06, right? 6 times 1.01, and then add in 1 oxygen, 16. So that's 46.08. There we go. So how many moles is that? I get 3.69 times 10 to the minus 2. And that's ethanol. That's how I abbreviate ethanol, ETOH. OH is the alcohol group, and ET is the rest of it. Let's do this one. 11.2 grams of oxygen. What's the magic number here? Well, 1 oxygen is 16, so 2 of them is 32. So we have 11.2 and divided by 32. 3.5 times 10 to the minus 1. 50. 3 significant figures. Times 10 to the minus 1 moles of oxygen. Okay? So how many moles of carbon dioxide will this produce? Well, what's the ratio? Right? Ethanol down here, carbon dioxide up here, 2 of these for every 1 of those. Okay. So 3.69 times 2 will be 7.38 times 10 to the minus 2. 7.38 times 10 to the minus 2 moles. That's for this one. Right. That will produce this much carbon dioxide. How about this one? What's the ratio there? If you have oxygen on the bottom and carbon dioxide on the top, there's 2 here and there's 3 there. So it's 2/3 of that value. I get 2.33 times 10 to the minus 1. All right? So this is 10 to the minus 1. That's 10 to the minus 2. This has to be bigger. That means this is limiting. And that's your answer. Now, the selection might be in standard notation, so you have to check, see what's possibility. Okay, so move the decimal place 2 to the left. So it's 0.0738. E's your answer. Okay? You have to be very methodical with these things. And even if you are, you've seen me make some monstrous mistakes just with little simple errors. So you have to be very methodical and practice a lot. All right, that was 6. Let's see, I better scooch this back over here. There we go. See, 5 and 6, 7. We'll look at 7 also. Oops, too far. There we go. All right. So it says that iron, what's this compound? Fe2O3. What's the charge on iron, right? It's a transition metal, so it's a type 2 compound. Oxygen is 2-, so that's 6- charges for oxygen. 6+ is required from iron, but there are 2 of them. So you divide by 2, and that means 3+ each. So it's iron 3 oxide. With a molar mass that's given to you, that's nice. Reacts with carbon monoxide and its molar mass according to this equation. Fe2O3 plus 3 carbon monoxide moles yields 3 moles of carbon dioxide plus 2 moles of iron. And let's see, is that balanced? They say it is. 2 iron here, 2 iron there, 3 oxygen here, plus 3 is 6 oxygen. So 3 times 2 is 6 oxygen. And then we have carbon left over, right? 3 carbons, 3 carbons. It's good. Now they're saying, after we have this balanced, they put that one next, don't they? 3 of these, 3 of these, CO2 plus 2 iron. Okay, now they're giving us 185.5 grams of carbon monoxide. React with excess iron 3 oxide. So excess here. There's plenty. Right? So we're going to say all of this is consumed. How many moles of iron will be produced? Okay. So we can't go anywhere with mass. We have to have moles. So we need carbon monoxide. And actually, they gave us the molar mass of Fe2O3, but we don't need it. What we need is the molar mass of CO, which is 28. All right, that is useful. Point 0. Yep. Okay. So now we just divide this into that, and we find out how many moles of carbon monoxide we start with. .625. All right, of carbon monoxide. So go back to the question. How many moles of iron are produced? So we need to cancel carbon monoxide and leave us with iron. So the coefficient of carbon monoxide is 3. And for, yeah, that's right. Carbon monoxide. I pointed the wrong one. This one here. And 2 for iron. So 2/3 of that number will be the moles of iron. 4.42. Wait a minute. 4 significant figures. 4.417. Grams of iron. Okay. How'd they get 4.415? Oh, I know. When I calculated this value, I left it in my calculator, and my calculator doesn't round it. So if you round it first and then do the calculation, you get 4.415 instead of 4.417. That's why I like to keep all those decimal places until the very end, because what they have experienced here in this answer is a rounding error. But test-taking technique, choose the best answer. And the best answer is E. All right. So let's see what's, let's see. You may have noticed intentionally left blank. Now, why would I do that? Well, as it turns out, when I first put these review documents together, I was using a test bank. And I got to looking at it afterwards. In fact, after I had already worked out every problem in my handwriting, you know, with the worked problems. That's also another document that goes with this. And I numbered them. And I discovered that number 9 was referencing materials that had not been covered yet. And rather than go back and redo everything and renumber everything, I just chopped it out and said, this one's blank because, well, I don't say why, but it's because we haven't covered that material yet. Probably has to do with gases, right? We haven't got to gases yet. And that was easier than redoing all of my handwritten work over again. So now we're going down to 10. There it is. So with this following equation, and we see, is it balanced? 4 nitrogens, 4 nitrogens, 12 hydrogens, 6 times 2 is 12 hydrogens, and 14 oxygens. So there's 8 of them here, and 6 of them here makes 14. So it is balanced. We've confirmed it. How many moles of ammonia will be produced, will be required to produce 11.9 moles of water? Okay. So this one's really not that difficult. I need to start with a clean board. Okay. So the reaction we're using is 4 ammonia, and I'm going to leave, they're all gases, so I'm going to leave that part out. 7 oxygens, 4 nitrogen dioxide, and 6 water. Okay. So we're given 11.9 moles of water are produced. All right. How many moles of ammonia are required? So that's the question. Moles of ammonia. Really simple, correct? This is just a simple conversion factor problem. 11.9 moles of water. Conversion factor has to cancel water and leave us with ammonia. Right. Coefficients: 6 water, 4 ammonia. So again, 2/3 of that value. .93 moles. Of ammonia are required to produce this many moles of water. Now, that's if 100% of this is converted into that, correct? In the real world, that never happens. There's always a loss, right? But we're not told that. So for this problem, you have to assume that all of it is converted over there. And that means the answer is D. Okay. So let's see, what's the next one I have marked? 13. Okay. This board is ghosting way too much. I'm going to do a quick cleanup. All right. If you ever have a stubborn board, an old board that ghosts really bad, Goo Gone is your choice. That will clean it up in a second. The problem is it cleans all the pores and leaves the pores open for more ghosting. So you have to seal the pores. Next item, WD-40. And even that is not perfect, but it helps. All right. Now, let's see, where was I? 13. Let's see if that helped any. 13. I may have left too much WD-40 on there. The unbalanced equation. Disodium silicon fluoride. Actually, shouldn't even have to say disodium. It's sodium silicon fluoride. This is a type 1 compound, except it's not binary, correct? Silicon and fluorine, they're both nonmetals. So my guess is that silicon fluoride might be a polyatomic ion. It's a possibility. Anyway, we combine that with sodium, metal, and that frees up solid silicon and sodium fluoride. All right, so let's write that reaction and balance it. Na2SiF6. And we'll leave ourselves a little bit of space here, just in case we need a coefficient. And then we have silicon and sodium fluoride. Silicon and sodium fluoride. All right. See, I'll switch to blue. Okay, now we need to balance this equation. And I think we're going to need a budget, so we better set it up right now. We're going to have sodium, silicon, and fluorine. All right. So we have 3 sodium here. We have 1 silicon, and we have 6 fluorines. So that's 6, 7, 10. 1, 7, 8, 9, 10. Then on the other side, we have 1 silicon, 1 sodium, and 1 fluorine. Okay, so we're gonna hold off on the elements till the end, right? Unless for some reason we need to use them right now. Well, actually, this sodium is in 2 places, so that may not help us very much. But that silicon by itself definitely needs to wait till the end. So where should we start? I would start with fluorines. Since sodium is in two places here, I wouldn't try to tackle that one first. Fluorine is 6 here, and we need 6 over here. Right? So that gives us 6 fluorines, and it gives us 6 sodiums also. Okay? How about silicon? Well, we've got 1 silicon here and 1 there, so we can leave that alone for now. And we've got 6 sodiums required. We're already 2 of them right here, so we need 4 more. So what if we put a 4 right there? That would be 4 plus 2 is 6. And we got 6 there and 1 there. It's balanced. So with a 4 here and a 6 there, and let's see, 2 sodiums, 4, 6, 1 silicon, 6 fluorine. Right. It's confirmed. Now let's remove all this stuff. That raises pretty good. All right. Now let's go to the other question. Now that it's balanced, we can do some stoichiometry. 3.09 moles of silicon are produced. 3.09 silicon. So 3.09 moles of silicon are produced. How many moles of sodium fluoride were also created? So we want to know moles of sodium fluoride. Right? You can go, you have any number of conversion factors that can be derived from a balanced equation. Just which ones do you need? Well, we start here and we end there, right? You can't go anywhere without moles. We already got moles. So we have this many moles of silicon. How many moles of sodium fluoride are also produced? Silicon's 1, sodium fluoride is 6. So we just 6 times 3.09. 18.5, 3 significant figures. Moles of sodium fluoride, because that cancels there. Okay, 1805 should be A. Okay. There's a little bit of ghosting here. We can tolerate it for a short time anyway. All right, that was 13. And let's skip down to 18. I got another blank one coming up here. 16, 17. There was another one that had material in it that we hadn't covered yet. 18. Okay. How many atoms of aluminum? How many atoms of aluminum can be produced by the decomposition of 31.5 grams of aluminum oxide? All right, here you go. The decomposition. Remember the types of reactions. Synthesis is combination of elements to make compounds. Decomposition takes the compound and makes elements. So if we decompose that, we're going to make aluminum and oxygen. Okay, so that's going to make 2 aluminums. Well, actually, no, because we got 3 here and 2 there. So we need to put a 3 here and a 2 here. Right? Cross multiply when you have an odd even. So that makes 6 oxygen, 6 oxygen. Now we have 4 aluminum required. Okay. Now, I'm wondering if we really need yeah, we do need the balanced equation, because we're going from 2 moles of this to 4 moles of that. So if we have 31.5 grams of aluminum oxide, how many moles is that? Grams, mole. So aluminum is 26.98 times 2, and then oxygen is 16 times 3. So that gives us the molar mass of aluminum oxide. .96. So we divide that number into 31.5. And I get 0.3089. That's moles of aluminum oxide. So convert that to moles of aluminum. Right? Aluminum oxide, aluminum, the ratio is 2 to 4, so it's twice that much, which is 0.6179. Moles of aluminum. So how many atoms is that? Moles on the bottom, right? And atoms on the top. So we have, for every mole, you have 6.022 times 10 to the 23rd atoms. Three point seven 3.72 times 10 to the 23rd. And that's why A is the answer. I can't help feeling that there's a simpler way to get there. This is moles of aluminum oxide. If we decompose aluminum oxide completely to aluminum, how many moles of aluminum for 1 mole of aluminum oxide? 2. Right? So we really don't need the equation. If you know that it's a decomposition, 2 times this value would give us that value. Right? So 6 of one, half a dozen of the other. Works both ways. And then you just convert moles into atoms. All right, that was 18. Let's see, next one on my top 40. Number 23. One more. There we go. I think we're starting to get redundant. Okay, the longer you leave it on here, the ghostier it gets. So now we got blue ghost. Maybe I need to switch back to black. In fact, I need to get a fresh marker. I think that'll help. Here we go. All right, 23. What's the mass of water produced when 9.47 grams of methane react with an excess of oxygen in the following unbalanced reaction? So we got to balance the equation. It looks like all the compounds and elements are written correctly. So we just need to balance the equation. Methane plus oxygen yields carbon dioxide first. Yep. Carbon dioxide plus water. Okay. Let's just be safe and make a budget. So we got carbon, hydrogen, oxygen. 1 carbon, 4 hydrogens, 2 oxygens. 6, 7, 4, 5, 6, 7. 1 carbon, 2 hydrogens, and 3 oxygens. So that's 5, 6. 2, 3, 4, 5, 6. Okay, now where do you start? Well, over there, oxygen's in 2 different places. And here they're odd and even. But notice, if we balance the hydrogens, two plus 2 is 4. Now it's even, right? We still only have, we don't even have to touch that one. We just say 2 makes 4. 1, 4, 4, 1, 4, 4. We're balanced. All right, now we can do some stoichiometry. 9.47 grams of methane is given. And the question is, well, we're also given excess oxygen, which makes sense. If you're burning methane in air outside, there's going to be plenty of oxygen. What's the mass of water produced? So we're looking for grams of water. In this case, you've got to go mass moles, moles moles, moles mass. So what do we need to know here? We need to know the molar mass of methane. 1 carbon, 12.01, and 4 hydrogens, 4.04. 1605.05. Divide that into 9.47. 0.590. 0.590 moles of methane. Now we need to convert that to moles of water. So methane converts to water 2 to 1. 2 waters, 1 methane. So we just say 2 times that value. 1.180, actually, 1.180 moles of water. Right? Cancel that one. Leaves us with water. Now we need to go back to grams. Moles, grams, molar mass again. So what's the molar mass of water? 18.02. Right? 16 for water, 2 times 1.01 for hydrogen. 18.02. And that should give us our answer. 21.3 significant figures. 21.3. 21.3 is right here. All right. Okay, let me mark that one off. And let's look at 26. You guys stop me anytime if you need to ask a question, or if I'm not clear. 26, unbalanced equation. Okay, we've got to balance another equation. And after we do that, we need to find out how many moles of water produced are needed to react with 206 grams of aluminum carbide. Right? When carbon is in the anion position, the second position, it's behaving like an ion. And since aluminum is positive, then the carbon has to be negative. So when we write 26, when we write like this, aluminum is always +3. And carbon as an anion would be 4-, right? If you move from right to left, halogens are -1, chalcogens are -2, nicogens are -3, carbon family would be -4. Under these circumstances, when it's in an ionic compound like that, aluminum carbide means 4-, which means 4 here, 3 there. So that's where the formula comes from for aluminum carbide. And then we're going to react it with water and produce what? Aluminum hydroxide plus methane. This would be a good product to use in a miner's lamp of a century ago, right before electric lamps. You just put some aluminum carbide in there and drop some water on it, and it produces methane. And then you just flick your lighter, and there you got a flame and light. Of course, you got an open flame in a coal mine, which is not a good idea. Okay, so let's balance this thing. Notice that we've got a polyatomic here, but it's not on both sides. So we have to break it apart. We can't keep the polyatomic as a balancing group. So let's just break everything apart. There's aluminum, there's carbon, hydrogen, and oxygen. In fact, for this problem, the real bear here is balancing this equation. Okay, 4 aluminums, 3 carbons, 2 hydrogens, 1 oxygen. So that's 3, 6, 10. 4, 7, 8, 9, 10. 1 aluminum over here, carbon, 1 carbon, hydrogens, 3 hydrogens here, and 4 there, 7 hydrogens, and oxygens, 3 oxygens, right? Don't forget the subscript. So that's 10, 11, 12. 4, 5, 6, plus 6 is 12, right? 2 times 3 is 12 atoms. 6 atoms makes 12. Okay, where do we start? Well, let's see. Oxygen occurs in one place over here, one place over there. Aluminum, 1 and 1. Carbon's in one place here, one place there. So maybe it won't be so bad. What if we balance the aluminums first? Right? if there's no obvious place to start, and we're going to keep water till the end if we can, even though this is an even and that's an odd, it might work out in the end. So starting at the top is not a bad choice. 4 aluminum. Now that changes the number of oxygens. So 3 times 4 is 12 oxygens. And hydrogens, 3 times 4 is 12, plus 4 is 16 hydrogens. Okay? And we still have 1 carbon. Now, how about the other side? Well, we're going to need 3 carbons. Right? So that gives us 3 carbons. Plus it changes the hydrogens. 12 plus 12 is 24 hydrogens. Correct? 12. 4 times 3 is 12. 24. Okay? So now, that's balanced, that's balanced. What we need is 24 hydrogens on this side. So what if we have 12 here? 24 hydrogens, correct? And 12 oxygens. It's balanced. That was the hardest part of this one question, was balancing that equation. So 1, 12, 4, and 3 gets us balancing coefficients. Now we can get to the question. 206 grams of aluminum carbide. 206 point. Oh, that's, well, yeah, you really don't need that decimal, right? That's a non-zero number. All of them are significant. Okay. And how many moles of water are needed? So we need moles here. So we need a molar mass for this one. Right? Grams, moles. So the grams cancel, leaves us with moles. So we got to add up 4 aluminums, which is 26.98. 26.98 times 4. And then 3 carbons, which would be 12.01 times 3. So that gives me 143.95. Divided into 206. 1.431. Of aluminum carbide. Then we need to convert that to moles of water. So aluminum carbide cancels, leaves us with water, and the ratio is 1 here and 12 there. So we multiply that value here times 12. I got 17.3 significant figures. 17.2 moles of water. Okay? And that's B is the answer. I'm curious, what would be the mass of water? I mean, out of 206 grams of aluminum carbide, what's the mass of water that's required? That's pretty heavy, right? To put in the cap on your head. So 17.2 and then 18.02 times, that's 310 grams. So it takes more water than aluminum carbide to make this thing work. So what is that, 500 grams? If you put that much in your cap, which actually would be too much. But if you did, you'd have 500 grams sitting on your head, pulling your cap down. 500 grams is almost a pound. Right? You wouldn't put that much in your carbide lamp. That's probably why they use calcium carbide instead. Calcium carbide is a lot lighter, right? 40, that's 80. 80 enter. Calcium carbide would be 2 calciums and 1 carbon. Yeah, it's only 92 grams to get the same job done. Actually, not the same job, because calcium carbide only has 1 carbon. All right, so it's a different chemistry. Okay, that was 26. Let's see, how am I doing there? Scooching a little bit there. 26. And the next one I want to do is 29. 29 is going to take some thinking. Okay. It's not impossible, but you do have to be methodical and think about it for a second. All right, consider the following reaction where X represents an unknown element. So we have 6X solid plus 2 B2O3. I think that's diborane. And that yields B4X3. Solid? Yep. Plus 3 XO2 gas. All right. The question is, what's X? Okay. What are we given? This equation is, we have to assume it's balanced. Since we don't know what X is, there's no way we can challenge that. So 165 grams of X reacts with diboron trioxide, okay, to produce 2.29 moles of this compound. 2.29 moles of that compound. That's everything we're given. All right, so if we're going to determine what X is, what do we need to know? X is an element, and these are our choices. Are we able to determine atomic number, which would be definitive for the element? No. We can't do that with the information given. So our next best bet is molar mass. What's the molar mass of X? What do we need to know to find the molar mass of X? We need to know the mass of X, and we need to know how many moles is that. Right? So we do need to know how many moles of X. So that's really the question. How many moles of X are there? Then we can calculate the molar mass. All right, what else are we given? We can't do it from here because we don't, I mean, it's circular. We can't find X because we don't know what it is. And we don't know what it is, so we can't do the molar mass. So we have to go to the other piece of information that's given. 2.29 moles of this compound is how many moles of X? You know what else we can do? The total moles here is the number of moles there plus the number of moles here. So this many moles of B4X3 is how many moles of X, right? For every one of these, you've got 3 of those, right? So if it's 1 mole here, then it's actually 3 moles times that. 27, 2 and 6 is 8, and 6, right? 27, 2, 6, 8, yeah. That's moles of X from here. How many moles of X from there? Well, this is 1 to 3, so this is going to be 3 times that. We've already done that calculation, 6.87 moles of that compound. How many moles of X is it? Well, it's the same, right? You got 6.87 moles of this and 1 mole per each. So you got another 6.87 moles of X, right? So the total then is, let's see if I can do this in my head. 1 to 16, 17, 1 to 12, 13 moles of X. So that's how many moles of X are on this side. How many moles of X are on this side? Exactly the same amount, right? Matter cannot be created or destroyed in a chemical reaction. So if you found out how many moles are on this side, exactly the same on that side. So we have 165 grams per 13.74 moles of X. Now let's see if that works. 165, 13.74. I get rounded off to 3 decimal places, 12.0. So which one of these has a molar mass of 12.0? Carbon, the closest one. So X is carbon. All right. That took a little brain power, I know. But it's good to exercise your brain every now and then, especially right before an exam. I want to do another one like this. It's not in the, it's not on the paper, but it'll give you a little more experience with working these kind of detective problems. So, we have this reaction. X is reacted with 3 moles of fluorine and gives us this compound. Okay, let's see, is that balanced? 1X, 6 fluorines. Okay, it's balanced. What else are we given? Well, you've got, I'm going to give you 235.2 grams of X. That's easy to determine. You just weigh it. And then also after the reaction, you can weigh the product. And the product is 347.9 grams. Now, we don't know if it's a gas or a liquid or a solid, right? We're just given that mass. So we can't deduce anything from the physical state. So what we have to do is find out, if we want to find out what X is, we need to know the molar mass. So we know how the mass of X, how many moles is it? So how can we get moles out of this? The only molar mass that we know in this reaction is fluorine. So if we could find out what the mass of fluorine is, we could determine the moles of fluorine. And then once we know the moles of fluorine, we can relate it back to moles of X, right? Because we know the ratio here. So how many grams of fluorine are there? During a chemical reaction, how do we approach mass? The mass of the products is equal to the mass of the reactants, correct? So that means if you start here with this many grams and you end up here with this many grams, what's left over? The grams of fluorine, right? The mass of fluorine. So if we subtract 235.2 grams of X, then we find out what the mass of that one is. So that's 0.7, that's 2, that's 1, that's 1. 112.7 grams. So now we know the mass of fluorine. How many moles of fluorine are there? Right. So you just say, right? So the grams will cancel. We need, what's the molar mass of fluorine? Well, how many fluorines are there? Actually, 2. Right? So the moles of fluorine gas would be 2 times the molar mass of fluorine. 19.00 times 2 is 38. Okay. So if we divide 38 into 112.7, we get 2.966 moles of fluorine F2. So what's the relationship between this one and that one? Because we need to find out how many moles of X there are. 3 to 1. So we get rid of fluorine and leave us with X. Right? This will cancel. And we have 3 here and 1 there. So 3 into that number. Divide 3 into 2.966. 0.989 equals 0.989 moles of X. So grams per mole would be divide this 989 there. Grams per mole. 0.989 into 235.2. 238. So you go to your periodic table and you follow molar masses. They get bigger from top to bottom and left to right. So you just follow along until you find something that's close to 238. We have to get way down into the actinides to get something that heavy. Looks like it's uranium. Okay. So they weren't exactly alike, really. You just have to understand how the stoichiometry works. We had to know that masses are conserved. So the difference between that one and that one has to be this one. It's the only possibility. Then that led us to our conclusion. From then, it was all downhill. By the way, the exam on this one's not going to be due until a week from Monday. week from Tuesday, actually, because next week is spring break, and the following week we won't meet until Tuesday. So you've got that Monday also, after spring break, to finish this exam plus the homework. So you've got plenty of time. Should be able to do a little at a time, so it doesn't burn your brain out. All right. There's plenty of time, it looks like. Let's see, 29, 32. Let's try 32. All right. 32. See how my position there. That's good. "32 says, which of the following reaction mixtures would produce the greatest amount of product?" And we're back to the Hobber process. Assuming all reactions go to completion, right? That makes sense. Each involves the reaction symbolized by the equation N2 plus 3H2 yields 2NH3. Okay, so our balanced equation is this one. Okay, and we have for A, 1 mole of N2 and 3 moles of hydrogen. One of these, 3 of those. I'm not going to write moles because it looks like, yeah, everything's moles. B, 5 moles of N2 and 3 moles of H2. 5 and 3. All would produce the same amount. So C means same for all product. D, 1 mole of N2 and 6 moles of H2. 1 mole of N2 and 6 moles of H2. Oops, wrong place. Sorry. 1, 6. And then E, 3 moles of N2 and 3 moles of H2. Okay. So with this information, this is 1 to 3. Those are stoichiometric ratios. Exactly 1 and exactly 3, which means exactly 2 would be produced. Okay? For this one, 5 and 3. So there may be a limiting factor here. 3 of these would require how many of these? Just 1, right? So this is excess. That's limiting, and 3 produces 2. On this one, 1 requires 3 of these, right? So these are excess, this is limiting, and 1 produces 2. 3 and 3, 3 of these requires 1 of those, so we have 2 moles excess here. That means 3 produces 2. So each scenario produces exactly the same amount. C is the answer. Okay, that's 32. That's down to 33. And see what that gives us. $33. All right. The balanced equation, that's nice of them. It's already balanced. Let's see, 4 phosphorus, 4 on both sides. Yeah, there we go. 4 there, 4 there, 12 hydrogens. 4 times 3 is 12 hydrogens. It's balanced. 5 moles of hydrogen. What does this reaction tell us? 5 moles of hydrogen, what? So we have to look at each one of these to see which one satisfies. Let's write the equation. P4 plus 6 hydrogens yield 4 phosphorus trihydride. All right, so 5 moles of hydrogen is given. So what do we have to select from? A, cannot react with phosphorus. I'm not even going to write that one up there. That's just ludicrous. If you've got a balanced equation and you've got 5 moles of hydrogen gas, they're going to react with the phosphorus. Reacts with 2.5 moles of P4. 2.5 mole of P4. Is that true? How much P4 is required? Well, 6 to 1, right? So if we have 5 moles of hydrogen and we convert it to P4, there's 1 there, 6 there, 5/6. That's less than 1, right? So that one can't be either. There's not a, that's the wrong ratio, right? It's going to react with 5/6 of a mole of P4, right? So how about C? Produces 3.3 moles of pH3. All right, so we got 5 moles of hydrogen. We're going to convert that to pH3. So what's the ratio? 6 of these and 4 of those. So 2/3 of 5. 20 divided by 6. Right. 4 times 5 is 20 divided by 6. Which would be reduced to what? Let's see. 2, this would be 3, 10/3. So that would be 3, 9, and 1/3. Right? That's true. And since there are no, except for cannot react with phosphorus, and that's ridiculous, then we don't have to do D and E. If you're in the middle of an exam, you find the right answer, go with it. Right? We already determined 3.3 moles of pH3 would be produced, so 10 moles of pH3 can't be. Reacts with 5 moles of P4. We already said that reacting with P4, it only requires 5/6 of a mole. So more moles go in the wrong direction. Right? So we actually did find the right answer in C. Right there. Okay. That's 33. And how about 39? Here we go. Ah, 39. Okay. Consider the reaction of magnesium metal with hydrochloric acid to produce magnesium chloride and hydrogen gas. Okay, so you got a word problem there, and you have to write the balanced equation, maybe. Let's see if we need it. 4.52 moles of magnesium and 4.52 moles of hydrochloric acid are reacted. How many moles of hydrogen gas are produced? Yep, we're going to need the balanced equation. So you write the correct compounds and elements first. Magnesium metal reacts with hydrochloric acid to produce magnesium chloride. Halogens are -1, alkaline earths are +2, so you need 2 chlorines. Right? That's a solid, plus hydrogen gas. All right. Now that we've written our compounds correctly and our elements, balance the equation. This one should be fairly simple. Right? Magnesium on both sides, 1 of them. We need 2 chlorines. 2 chlorines. 2 chlorines, 2 hydrogens. It's balanced. Right, so that was simple. Now what are we given? 4.52 moles of magnesium and 4.52 moles of hydrochloric acid. Right? Then the question, how many moles of hydrogen gas are produced? Okay, that tells me that we need to find a limiting reactant. And since we're going to a product, we'll use my preferred method. Right? So how many moles of hydrogen gas can be produced from this many moles of magnesium? This would produce 4.52 moles of hydrogen gas. Right? 1 to 1. There you go. How about this one? 4.52, 2 to 1. So we would do something like this. We get rid of HCl, because that's what this is, and hydrogen here, which is 1 and 2, which is half of that. So it would be 2.76. 2.76 moles of hydrogen gas. That's the limiting one. So there's your answer. 2.76. Oh, I did it wrong. Sorry. I should have used my calculator. 2 divided into that is 2. 2 into that's 2, 6. Yeah, 2.26. My mistake. C is the answer. All right, 39 is done. And let's get this back on screen there. Okay, so that was 39. Let's see what else we got. I got marked off here. 43. Let's try 43. Here we go. All right. 43. Based upon this balanced equation, we can check ourselves. See, 4 nitrogens, yep. 12 hydrogens, 14 oxygens, that's 8 plus 6 is 14. It's balanced. So 4 ammonias plus 7 oxygens yields 4 nitrogen dioxide and 6 water. Okay. How many molecules of water are produced if 9.12 moles of NO2 is given off? 9.12 moles of nitrogen dioxide are released in this reaction. How many molecules of water? So we don't want to just know moles, although that's an intermediate step. We want to know molecules of water. So how many moles of water are there? 9.12 moles of NO2, right? Moles, we'll just say NO2 and H2O. So there's 6 here and 4 there. So that's moles of water now. How many molecules of water? So we have moles of water. We want to know molecules of water. So now we cancel this one, this one, this one, this one. And this is 6.022 times 10 to the 23rd. So that way we can do it all in one calculation. 9.12 times 6 divided by 4, and then times 6.022 10 to the 23rd. So I get 8.2, 3 significant figures, 8.24 times 10 to the 24th. Is that right? Yeah. Let's see if that's one of them. There it is right there, D. Okay? You don't have to do it in one step. You can find out how many moles of water and then go to the next step and do molecules. I just want to do it all at once. So I did a chained conversion. All right, 45. Let me see, we ought to be getting close to the end. 45. We're going to finish early today, I think. 45. It's like I said at the very beginning, so many problems in chemistry can be solved with dimensional analysis, conversion factors. The key is understanding the chemistry behind them, because sometimes you can't just use a conversion factor, because if you use the wrong conversion factor, you get the wrong answer. So you need the chemistry to go along with dimensional analysis to get the job done. But the calculation is simple once you've identified the chemistry that goes with it. Okay, so 10,2-fluoride, right? So we have to write that compound. It looks like it's already written for us. 10,2-fluoride is added to some dental products to help prevent cavities. Right? That's how they get fluorine into your toothpaste. Manufacturers have to make 10,2-fluoride first, though. And this is how they do it. They take tin, metal, and they react it with hydrochloric acid, which is extremely aggressive. And it makes 10,2-fluoride, and it gives off hydrogen gas. Okay, how many grams of 10,2-fluoride can be made from 49.6 grams of hydrogen fluoride? They should have said hydrochloric acid because it's aqueous. Right? But now technically that's okay. 49.6 grams of hydrogen fluoride is accurate. If they had said volume of HF, it would have been hydrofluoric acid. But since they're saying grams, they're actually looking at the mass of that compound and not the state that it's in. So they're saying there's plenty of 10, right? 10 is excess, hydrofluoric acid is limiting. And when it runs out, the reaction stops. 49.6 grams of hydrogen fluoride. All right, so here's the equation. 45. Right. We've got 10 plus HF yields aqueous, excuse me, aqueous. That is soluble. And hydrogen gas. All right, let's see if I got all my coefficients in there. Yep. So we're given 49.6 grams of hydrogen fluoride. And the question is, how many grams of 10,2 fluoride can be made? How much of this? So we got to convert this to moles, and then moles of this to moles of that, and then moles of this to mass of that. So we need a molar mass of HF, 49.6 grams of HF is converted to how many moles? Okay. So we need hydrogen plus fluorine. Fluorine is 19.00. And then hydrogen is 1.01. So that's 20.01. Okay. And 49.6 divided into it is 2.479 moles of HF. Now we need to convert that to 10,2 fluoride. And we have two of these, one of those. So half of that number is 10,2 fluoride. 1.239. Right. So now to convert that, moles on the bottom, which will cancel these moles, grams on the top. So 10 is right in here, 118.71. 118.71 plus 2 fluorines, and each one is 19. So 156.71. 156.71 per mole times 1.239. I got 194. Three significant figures. Okay, there it is right there. That was 45. Okay. Let's see what else. There's another blank one. Oh, there we go. Went all the way over to 60. And there we are, right there. Oh, an A, B, C, D problem. Hypotheticals. Okay. I can do that. When we're using ABCs instead of actual compounds and elements, sometimes you have to make some assumptions. Well, what do they mean? Do they mean that A is an element or A is any compound? Don't know. You just have to assume that it doesn't matter. Consider the following reaction. Okay, 60. 2 A's plus a B yields 3 C's plus a D. Okay. 3.35 moles. And it's already balanced. We have to assume that because, I mean, how are we going to tell? We have to take their word for it. 3.35 moles of A and 2 moles of B react to form 4 moles of C. What's the percent yield of this reaction? Okay. Remember the definition of percent yield is, well, actually the way we defined it in class was the mass of the product actually obtained, the actual mass, divided by the theoretical mass times 100. In this case, we don't have mass. So we're forced to use moles. So we just have to find out how many moles of C would we expect to obtain. This is the actual. What's the theoretical? That's the question. All right, so we have to find the limiting one, right? We've got amounts of both A and B. One of them's going to run out. So we take 3.35 A and we convert it to C. So 3 C's, 2 A's, 1.5 times 3.35 is 503. 5.03 of C. With 2, B we have B here, C there. We have 1 B and 3 C's. So that will be 6 C's. Which one's limiting? Well, A produces the least amount. So A is limiting. Runs out then. We can't use all of B to make 6C because A would run out. So it's 5.03 is the theoretical. Now we do the calculation. Actual divided by theoretical times 100. I get 79.5. Percent. Is anything close to that? Yep. That one's pretty close. 79.6. So that's your best answer. Okay, let's see. Better scooch that back a little bit. That was 60. 61. Let's see. Is this going to help us any? Calculate the molecules of oxygen required to react with 25 grams of sulfur in the following reaction. Okay. So our balanced equation is 2 sulfur plus 3 oxygen yields 2 sulfur trioxide. Let's see, this is a gas, this is a gas. All right. And we need 25 grams of sulfur is given. And the question is, molecules of oxygen required. Molecules of oxygen required. So how many moles of sulfur are there? Sulfur is 32.07. That gets rid of grams and makes moles of sulfur. Now, sulfur converted to oxygen. 2 sulfurs, 3 oxygens. So that gives the moles of sulfur to moles of oxygen. And then moles of oxygen to molecules. Okay? So let's see, 25 divided by 32.07 times 3 divided by 2, and then 6.022 10 to the 23rd. So I get 7.04 times 10 to the 23rd. Molecules of oxygen. There you go. How many atoms of oxygen is that? Exactly twice as many, because the molecule of oxygen has 2 atoms each. All right, so that was 61. Let's see, are we going to do any others? Yep, getting close to the end. We're ghosting up pretty bad here. Okay, next one, 69. There it is. All right, 69. Let's start way over here. I have a feeling this one's going to take some room. In the reaction between carbon monoxide and Fe3O4, the theoretical yield in an experiment is calculated to be 47.2 grams. A careless chemistry student carries out the experiment. The actual yield is 37. Calculate, oh, it looks bigger than it is, right? So when we react, and this reaction produces iron, right? The theoretical yield is calculated to be 47.2 grams of iron. You don't even have to have a balanced equation, because the theoretical is 47.2 grams of iron. But this student only got 37. So the theoretical yield is 78.4%. Okay. So even I was fooled. I thought this was going to be a big problem, but it's not. Calculate the percent yield. You're given the theoretical, you're given the actual, just do the calculation. All right. 70 is also on my list. So let's look at 70. What is KClO3? See, remember your polyatomic ions? I always start here. Chlorate, chlorite, hypochlorite, perchlorate. This is chlorate. Potassium chlorate is the compound. For 70, potassium chlorate is decomposed by this reaction. 2 potassium chlorates yield 2 potassium chloride plus 3 oxygens. How many moles of oxygen are formed, assuming 100% yield, if you start off with 3.1 moles for this one? Oops. 3.1 moles. Actually, we're going backwards. This is simple. How many moles of oxygen with 100% efficiency? That's just theoretical all the way across. 3.1 moles of that are related to O2 by their coefficients. So 1.5 times 3.1. 4.7. 2 significant figures. All right. So that's why E is the answer. Okay. Ooh, we're going to do the whole next page. I hope there's something new here. '71. .4 moles of iron react with chlorine, according to this balanced equation, and we can check it, right? 2 irons, 2 irons, 6 chlorine. 2 times 3 is 6 chlorine. That's balanced. According to this reaction, .4 moles of iron. Okay. React with chlorine. How many moles of chlorine are required to react with all the iron? Fairly simple, right? So we're really just, it's too simple. Iron to cancel, chlorine here. So the ratio is 3 to 2, right? So what's a half of 3.4? 1.7 times 3. 2 and 3 is 5. 5.1 moles. Right there. Okay. 72. Let's see if 72 gives us more challenge. By this time, you ought to be getting bored with these problems, which is a good sign. If you're bored working a particular type of problem, that means you know it. 72. Ammonia reacts with oxygen to form nitrogen dioxide and water, according to this reaction. So, kind of them, it's already balanced. We can check for ourselves, but it looks like, let's see, 12, yeah, that's balanced. You react ammonia and oxygen, and at the end of the experiment, you find you produced 23 grams of water and 8.52 grams of ammonia left over. What's the mass of oxygen that's reacted? All right, so we have 4746, 4, 7, 4, and 6. And you find 23 grams of water at the end and 8.52 grams of ammonia left over. That's how much remains of ammonia. Now, maybe we don't need that information. Let's look at the question. What's the mass of oxygen that was reacted? We don't need that, do we? We already know how much of water is produced. If we know the moles here, we can find the moles there and then convert back to mass. So there's blue smoke in this problem. It's blown in your face, try to confuse you. That's why putting it up on the board like this extracts the information so that you can see it more clearly. Word problems are meant to confuse. 23 grams of water converted to moles . 18.02 divided into 23 for water. 1.276. 1.276 moles of water. So how many moles of oxygen is that? So we have water on the bottom, oxygen on the top. I'm going backwards. So we have 7 oxygens for every 6 waters. So what is that? .49, 1.489 moles of oxygen. Now we just have to convert to mass. So for oxygen, O2, they're 2 times 16, 32. So 32 times that number is 47.7. Grams of O2. There it is right there. We didn't even need to know this, not to answer that question. A different question, yeah, maybe you did need it. Okay, so that was 72. 73. Here we go. '73. For this reaction, C2H4. You don't know what that is. That's ethylene. sometimes called ethene, plus oxygen yields carbon dioxide and water. All right, so we got that reaction to guide us, C2H4. Takes 3 oxygens to yield 2 and 2. 2 CO2s plus 2 waters. That compound is actually like that. So you got the carbons bound together by a double bond, and then you got the hydrogens around there like that. Okay, what are we given? 5.5 moles of CO2 are produced. 5.5 moles. Then what's the question? How many moles of oxygen were reacted? Okay, fairly simple. 5.5 moles of this converted to moles of oxygen. So there are 3 here and 2 there. So 1.5 times, 3 times divided by 2 of 5.5. 8.25. Best answer. You know what? Oh, I do have to round it off, because it's only 2 significant figures. So actually it should be 3. Now, the best answer, I would think, would be C. But since you have none of these, if you put D, then you would be correct. Because 8.3 is not 8.2. So that's something to consider. And I need to remember that when I'm grading papers, right? If none of these is an option, and the answer that you get from the calculation is not exactly one of the others, then none of these is a valid answer. All right, 75. Here we go. Let's see. We did this one before, didn't we? We balanced that equation, but maybe we didn't do the exact same calculation. All right, so we're going to need a balanced equation for this one, C2H5OH, and then O2, and carbon dioxide, and water. Okay, so I wonder if I can do this without the budget. I'll get a shot. 2 carbons here, so 2 carbons there. So that means 2, 2. That means we've got 4, 5 oxygens, but we have 3 oxygens over here. How about hydrogens? We got 6 hydrogens here. All right, so that's 6 hydrogens, taking care of that, taking care of the carbons. Now we have 4, 7 oxygens. And over here we have 2 and 3. So if we say 3 times that, that would give us 6 oxygens plus 1 is 7. So let's check it to see. 2 carbons, 5, 6 hydrogens. 1 plus 6 is 7 oxygens. 4 plus 3 is 7 oxygens. Okay, so we're balanced. Now, what's the question? 1.86 grams of ethanol. react with 14.3 grams of oxygen. All right. How many moles of water are produced? All right. Here we have two definite amounts of reactants, and we need to know the product. That screams limiting reactant. One of these is going to run out. And since we're producing a product, the most efficient course is to say, all of this converted to that, how much is it? All of this converted to that, how much is it? The least amount is your answer. So we need an ethanol molar mass, 2 carbons, 6 hydrogens, and 1 oxygen is 46.08. Okay, so the grams cancel and leave us with how many moles? Zero point four 0.0404. 0404. Okay. How about this one? How many moles of that are there? Oxygen, 2 of them is 32. So 32 into 14.3 is 0.447. See, is that reasonable? Well, it's about half of this. Yeah, that's reasonable. How about this one? 2 divided by 50 is about 0.02. So we got the right number of decimal places. That's good. Let me do that calculation again. I just have a sneaking suspicion. Now that's right. Okay, now we need to convert that to water. So we have 3 oxygens, 3 waters. It's exactly the same amount. So this is also 0.447 moles of water. How about this one? This one will be times, so 3 waters and 1. So we need 3 times that. So 3 times 0404 is 0.121. Right? Compared to 0.4, this is the least amount. So that's the limiting one, is 0.121. Right there. All right, let's see if we got any others that I've checked off here. Yeah. See, is that the last one? Nope, I got 3 more. Yep, 3 more. Go to 80. Here we go. Number 80. You react 22.5 grams of nitrogen with 22.5 grams of hydrogen. Determine the mass of ammonia. So in the wording of the problem, we're saying the reactants are nitrogen and hydrogen. The product is ammonia. That's it. We're talking about Hobber, of course. So that's 3 and that's 2. And we've got 22.5 grams here and 22.5 grams here. All right. So we need to convert that into moles. Why don't we do it like this? All right, do this one here. So what's the molar mass of nitrogen? Well, 14.01 times 2 is 28.02. So that's 0.803, 0.803. And then we convert that to ammonia because the question says, determine the mass of ammonia that can be produced. We got to find the limiting reactant. We've got a definite amount of this and a definite amount of that. So one of them is going to run out. So N2 to N3 ratio is 1 to 2. That means we have 1.606 moles of ammonia. If all of this reacts. If all of this reacts, hydrogen, right? Grams per mole, 2.02. Because there are 2 of them. (22.5) enter, and 2.02 divide. That's 11.14. Moles of hydrogen. And then we convert that to moles of ammonia. So hydrogen cancels, leaves us with ammonia, and we have 2 here and 3 here. So 2/3 of that value is 7.43. 7.43 moles. All right. Now we know the limiting one. It's nitrogen. We're only going to get this much ammonia. So, how many grams is that? Molar mass of ammonia. 14.01 for nitrogen and 3.03 for the 3 hydrogens is 17.04. Times 1.606. $27.4. Okay, so is that on the list? Okay, I read it wrong, didn't I? No, okay, I'm looking at the wrong one. Duh. 27.4, there it is. My eyes were drawn to this 247, and it's 27.4 grams. That's correct. Okay, 2 more to go. Those are all the ones that I've picked out. And the next one on the list would be 83. One more page. Here we go, 83. You know, that one looks familiar. Haven't we done this one before? We've used that same reaction. Let me look back here. Fe2O3. Here it is. Number 7. Let's see. Oh, it's a different. It's the same type of problem. It's just different amounts. 470 grams of Fe2O3, and here in number 7 is 185.5 grams of CO. Okay. So it's using the same balanced equation. You're just given different starting point. And you're going to end up with predicting the number of moles of iron. So we might as well work it then. Let's see. This reaction plus 3CO, 3CO2 plus how much iron? 2. Okay. So we're given 470 grams of this product. 470 grams. This reactant, excuse me. Excess. All right. Number of moles of iron that is produced. Okay, so we want to know moles. All right, so really all we need to do is convert this using the given information here. 159.7 grams per mole. So divide 159.7 into 470. Uh, 2.943. Then we want to convert that to iron. So the ratio is 2 irons for every one of these. So it's just 2 times that. 5.89, 4 places, 5.886. Cancel these 2. Okay, so there's your answer. C. And we got one more on my list. 84. And that's everything that I have marked off. A4. Yeah, A4. All right. Which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? This is ethane, 2 ethanes plus 7 oxygen. There should be a plus sign right there. Yields 4 carbon dioxide and 6 water. So none of the statements are true, well, we'll have to see about that. Let's see, 2 ethane plus 7 oxygen yields 4 CO2 plus 6 water. Okay. Yeah, that's good. All right. B. We'll come back to A if we need to. If we have an equal number of moles of C2, H6, and O2, there's no limiting reactant. Equal number of moles of this one and that one. If the equal number of moles, which one runs out first? C2H6 is limiting. What B is saying is if there's no limiting reactant, then equal number of moles, 1 to 1, is stoichiometric. But the stoichiometry is 2 to 7. So B is false. It cannot be true. How about C? If we have equal masses of C2H6 and O2, there's no limiting reactant. Now we have to work a little bit. Equal masses. So we have X mass there is equal to X mass there. Okay? So if the ratio of these two to one another is 2 C2H6 to 7 O2, then convert each one of these to, and this is grams, convert each one of these to moles, grams, moles. So oxygen is 16. Ethane is, let's see, 12.01 times 2 for oxygen. And then 6 hydrogens is 30.08. Is 30.08. Right? So this is 2 over 30.08 divided by 7 divided by 16. So 2 enter 30.08. So the numerator is 0.665 and the denominator is 0.4347. So divide those two and we get the ratio is 0.15. So if the mass ratio is 1 to 1, 1 to 1 mass, the mole ratio is 0.15 to 1, 0.15 to 1. So what does that mean? For C, if we have equal masses, there's no limiting reactant. All right, so if this is the ratio, what's the ratio of 2 to 7? So if this is not 2 to 7, it has to be that. What's 2 divided by 7? Is 0.29. So that's not the right ratio. Right? 2 to 7 is the correct ratio. This is the ratio that's given with equal masses. So C is wrong. How about D? If we have more mass of O2 than C2H6, then C2H6 must be the limiting reactant. All right, so go back to C. This is equal masses. What if we have more mass of O2 down here? What would that do to the ratio? If you increase the denominator, you decrease the quotient. So it would be less than 0.15, which is still not stoichiometric, right? So D is wrong. How about E? If we have more mass of C2H6 than then O2 must be the limiting reactant. Okay, more mass of C2H6 makes this a bigger number. Actually, we need to look at that may not be the best approach. The approach that I took. Let me check something here. Yeah, there's a better approach. Actually, it's not too far from what we've determined so far. The stoichiometric ratio is 7:2. Right. Or if we put oxygen on top, that would make a whole number. 3.4. So the ratio of moles of oxygen to moles of ethane is 3.2 to 1. No, 3.4, excuse me, 3.4. That's mole. So what does that mean for mass? Well, we have to just flip this over and say moles then converted to mass would be 16 grams per mole divided by 30.08 grams per mole. Right? So what's 16 times 3.4? 3.45 actually. And then divided by 30.08 is 1.83. So now the ratio is 1.83 to 1 for mass. Now we can make a comparison. These are stoichiometric ratios, 1.83 grams of oxygen for every gram of ethane. Now let's go back and look, because we're talking about masses here. If we have equal masses of C2H6 and O2, there's no limiting reactant. Well, we know that's wrong, right? Because equal masses is not 1 to 1 here. We need 1.8 to 1. So that can't be right. D, if we have more mass of O2, then C2H6 must be the limiting reactant. Not necessarily. It has to exceed 1.83, right? You can't just say more mass and call it limiting, right? Because it has to exceed that ratio. You have to have, if you want to make this the limiting reactant, then you have to exceed the ratio of oxygen to ethane by 1.8. So we can't say that either. How about E? If we have more mass of C2H6, then O2 must be the limiting reactant. Right. Now then you are exceeding the amount of 1.8 to 1. In that case, oxygen does become limiting. So E is the best answer for this one. That took a lot of brain power. And you may still not be convinced. That's possible. That's one way to work it. The other way is to take each of those mass assumptions here and work your way back to the mole ratio and see what the mole ratio looks like. That's the other way to do it. Okay. Well, that's all I have. If you guys have questions or comments or issues, we've got time to deal with them. 11:43, and we usually go to what, almost noon, right? 11:50. Oh, so we're not too bad. Now we got 6 minutes to go.